Earthquakes, those sudden and often devastating jolts from below the Earth's surface, can turn cities into rubble in moments. For centuries, people have sought to predict when and where the next big earthquake might strike to protect lives and property. Yet despite all the advancements in seismology, earthquake prediction remains one of the greatest challenges in science. In this video, we'll take a deep dive into the world of earthquake prediction, what scientists know, the methods they are testing, and why forecasting earthquakes is so incredibly difficult. Understanding the Earth's dynamic crust. To understand why predicting earthquakes is so difficult, it's essential to grasp the basics of how earthquakes occur. The Earth's crust is broken into massive plates, known as tectonic plates. These plates float atop a semi-fluid layer of molten rock called the mantle. The plates move slowly, at rates of a few centimeters per year, driven by heat from the Earth's core. The boundaries between these plates are often zones of intense pressure and stress. When the plates grind against each other, energy builds up until it is released suddenly in the form of seismic waves. These waves cause the shaking that we feel during an earthquake. The challenge with predicting earthquakes lies in understanding exactly when and where this built-up stress will be released. While scientists can track the movement of tectonic plates and identify fault lines, they have yet to find a reliable way to predict when an earthquake will strike with any precision. Current methods of monitoring earthquakes. Let's explore some of the methods used today to monitor and forecast seismic activity. Seismographs and earthquake networks. Seismographs are instruments designed to detect and record the intensity, duration, and frequency of seismic waves. These devices are deployed in networks across the globe to continuously monitor tectonic activity. By studying the data collected from seismic waves, scientists can determine the location and magnitude of an earthquake after it happens. However, while seismographs are critical for early detection, they don't provide enough information to predict earthquakes beforehand. GPS and ground deformation monitoring. Another promising method for understanding earthquake risk involves the use of GPS technology to track the movement of tectonic plates in real time. Precise GPS systems can measure even the smallest shifts in the Earth's crust, which can indicate where stress is building up. One example is INSAR, interferometric synthetic aperture radar, which is used to measure ground deformation by bouncing radar waves off the Earth's surface from satellites. If certain areas show signs of increasing strain, it could suggest that an earthquake is imminent. Still, while ground deformation provides hints, it's not definitive proof that an earthquake will happen soon. Can we use historical data to predict earthquakes? One of the key ways scientists try to forecast future earthquakes is by studying past events. The recurrence interval, the average time between earthquakes along a fault, is an important metric. By examining the history of quakes in a region, scientists can estimate when the next one might occur. This method, however, has its limitations. For instance, the San Andreas Fault in California is one of the most studied fault systems in the world. Geologists know that this fault is responsible for major earthquakes, and historical records indicate that large quakes happen roughly every 150 years. However, just knowing this doesn't help much in predicting exactly when the next big quake will happen. Earthquakes don't occur like clockwork, and many factors contribute to whether stress is released as a minor tremor or a major quake. In some areas, faults can stay locked for centuries, quietly building up stress. When they finally do slip, the result can be catastrophic. For example, the Tohoku earthquake that caused the 2011 tsunami in Japan occurred along a subduction zone that hadn't had a major quake in over 1,000 years. The lack of recent seismic activity made it challenging to predict. Early warning systems. What we can do. While precise prediction is not yet possible, scientists have developed early warning systems that can provide short-term alerts in regions prone to earthquakes. These systems don't predict quakes, but detect them in progress and send warnings seconds to minutes before the shaking reaches populated areas. Here's how they work. Detecting primary waves, P waves. Earthquakes generate different types of seismic waves, the most important being primary waves, P waves, and secondary waves, S waves. P waves travel faster but usually cause little damage, while S waves arrive later and are responsible for the destructive shaking. Early warning systems detect P waves and send out an alert before the more damaging S waves hit. This can give people precious seconds to drop to the ground, take cover, or even stop trains, close gas lines, and take other safety measures. Successful early warning systems, Japan and Mexico. Countries like Japan and Mexico have invested heavily in earthquake early warning systems. Japan's J-Alert system uses a network of seismic sensors to detect earthquakes and issue alerts. This system is credited with saving lives during the 2011 Tohoku earthquake, providing about 15 seconds of warning before the devastating shaking began. Similarly, Mexico's seismic alert system, SASMEX, is designed to provide early warnings, especially in Mexico City, which is highly vulnerable to earthquakes. Residents of Mexico City receive warnings of up to 60 seconds, giving them time to evacuate or take cover. While these systems are life-saving, they still rely on detecting earthquakes once they've already begun, rather than predicting them before they happen. Conclusion: is earthquake prediction possible? While true earthquake prediction, pinpointing the exact time, location, and magnitude of a future quake, remains out of reach, researchers are making strides in monitoring and reducing the impacts of earthquakes. Early warning systems and advancements in technology offer hope that one day we may be able to provide accurate forecasts. Until then, our best defense remains preparation, education, and resilience in earthquake-prone areas.